Collector and District Magistrate Shri V. Vinaychand IAS. Shri Adip Banuji Rao, Member of
అదే రావట్లేదు.
Destiny, Visakhapatnam is one of the oldest colleges in India, established by late Sri Ankitam Venkata Narasimha Rao in the year 1860 to cater to the education needs of the east coast of India. The college is located in a sprawling 11 acres land in the heart of the city of Visakhapatnam. The college has been re-accredited third cycle by NAC with A grade in September 2019. The college is under RUSA 2.0. The vision of the college is quality education for all, and the mission is to create a thriving community for the development of education, culture, and social values. The chairman of the management committee is the collector and district magistrate Shri V. Vinaychand IAS. Shri Adip Banuji Rao, member of the donor family, is the correspondent of the college. Professor Dr. D. Vijay Prakash is the principal of the college. There is a school in the college which is known as AVN High School. In post-graduation section, we have MCOM. Next, we have AU Distance Education Study Center, DLED, Diploma in Elementary Education, certificate courses like Information and Computer Technology, Tally, and Python are also available. This is the central library equipped with modern amenities and contains 1 lakh books. This is the sports block where we have excellent playground, sports facilities, indoor stadium, sophisticated gym, and the students of our college have participated in competitions conducted in various countries and won laurels. The college has well-equipped smart classrooms, internet facility to all the departments, special classes for slow learners, highly qualified, vast, experienced and dedicated faculty with 38 doctorates, special classes for SC, ST, BC and minorities, and merit scholarship sponsored by the management and public undertaking sectors as a part of corporate social responsibility. And for the security of the students, we have security systems, 60 CC cameras and anti-ragging cell. Other than studies and education, various other activities are conducted. like cultural activities on various occasions. We have 4 NCC units. One is exclusively for girls, 6 NSS units who are serving the society, then Ankitam Film Club and Ankitam Literary Association. There is JKC and Placement Cell, which trains and helps the students for placements in various corporate companies and other jobs. The courses offered in degree sections are BSc with Maths combination, Maths Physics Chemistry, Maths Physics Statistics, Maths Physics Electronics, Maths Physics Computer Science, Mathematics Statistics Computer Science, Mathematics Electronics Computer Science, and BSc with Biology combination, Chemistry, Botany, Zoology, BA with History, Economics, Politics, History, Politics, English Literature, History, Politics and Telugu Literature. In intermediate sections, we have Science, Arts and Commerce. Under Science, MPC English Medium and Telugu Medium, BPC English Medium and Telugu Medium. Arts and Commerce, CEC English Medium and Telugu Medium, HCT English Medium and Telugu Medium, HEC English Medium and Telugu Medium, MEC English Medium and Telugu Medium. Some of the illustrious alumni of the college are Sir C.V. Raman, the only Nobel laureate in physics from India, Padma Vibhushan, Professor C.R. Rao, the world-renowned statistician, Sri, popular Telugu poet, Alluri Sita Ram Raju, the great freedom fighter from Andhra Pradesh, Sri L.V. Subramaniam, IAS, Sri K.J. Rao, former Secretary, Election Commission of India, Sri Chakindi Koteswar Rao, popular preacher of Hinduism, Professor M. Gopal Krishna Reddy, former Vice Chancellor of Andhra University, cine actors like Padma Shri, Sri S.V. Ranga Rao, Devadas Kankala, Gollapudi Marithrao, K. Jaggaya, and politicians like Sabam Hari, Dharmanna Prasad, Dronam Raju Srinivas. All the mayors of the city of Visakhapatnam, former and present judges of High Court, many IAS and IPS officers, professors, and some popular film actors are the alumni of the 158 years old institution.
So, thank you very much for patiently viewed our college video. So, the inaugural section concludes. Now we are starting our technical section. We have a wonderful lecture by Professor Rajasekar Garu.
Yes, sir. Hello?
Sir. 1 minute, sir. It's a small introduction.
Excuse me, Professor Ramakrishna.
Yes, sir.
I'm not able to get the window to share the file.
Okay. So 1 minute, sir.
Now 1 minute.
Now I request Professor C. Srinivasan, head of the department, to introduce our innovative speaker, Professor Rajasekar, sir.
I think that's
over to Professor Srinivasan.
right.
Professor Srinivasan. Professor Srinivas garu. Professor Srinivas, head of the department.
మ్యూట్ లో పెట్టేసి ఉంటాడు.
Okay. Professor Srinivas garu.
Good morning to all. I am very much thankful to the organizer, first of its kind. I am going to introduce the eminent personality, Professor GP Rajasekar garu, Department of Mathematics, IIT Khargapur. Our hearty welcome to you, sir. It is an honor to introduce this magnificent personality. He completed his Masters in Applied Mathematics in 1992 at University of Hyderabad. Finished MPhil in the same subject at the same university in 1993. Subsequently registered for PhD and attained doctorate in 1997 in mathematics, fluid mechanics at the University of Hyderabad. He has an astronomical academic experience from January 1997 to November 1998.
You can make it short if you don't mind. Can you make it short introduction? It's available on web. People know. Okay.
Worked as a guest faculty at the University of Hyderabad from November 1998 to December 2000. JSPS postdoctorate fellow, applied physics, Tokyo University, Japan. He was visiting faculty at IIT Khargapur from 2 years. He then started teaching as assistant professor in IIT Khargapur.
హలో,
It takes only 1 minute.
ఎవరు?
He has an awesome, inspiring academic career.
విజయ్ భాస్కర్
Since
రెడ్డి.
1990 to 2018,
Can you mute
he has
your?
been receiving many awards, honors, and recognitions like JRF, SRF, Young Scientist Award in Mathematical Sciences, Mathematicians of the Year, JBS Gold Medal, and so on. With all his academic excellence,
లేదు, ఇప్పుడు
he
బ్యానర్
became
పెట్టారు, దానివల్ల కనిపించట్లేదు.
expert member
మళ్ళీ
in national committees
మళ్ళీ
like
చూస్తా ఉన్నావా?
Program Advisory Committee on Mathematical Sciences, Government of
కూర్చున్నా
India,
కూర్చున్నా.
Expert Committee for Mathematics Research,
బాగున్నారా?
Impact Center Support Scheme, Government of India. Beside he rendered service
క్లియర్ కనిపిస్తున్నారా?
academics and societies. Hope the
రెడ్ కర్టన్స్ ఉన్నాయి.
participants
May I
will
request
note the
Gandhi
contents
to
of
mute?
his deliverance. Thank you, sir.
You're on a phone call. Can you mute, sir? Mr. Gandhi.
చూస్తున్నాను ఒకసారి.
I request all the participants put your audio mute, please. So thank you, Professor Srinivas garu. Nice introduction of our an excellent renowned professor, Professor Rajasekar garu. So any questions after the end of this section? So don't disturb me.
చూస్తున్నాను ఎవర్రా అని.
Sir, that
Gandhi garu close cheyandi.
Gandhi garu can be mute, no? He's on a phone call. Can he be mute?
Gandhi, go to mute. Gandhi, mute loki vellu.
Mute everyone.
So, sir, so can I start?
So I request Professor Rajasekar garu
So
to start your session, sir.
During my lecture, you want me to be visible, or you want me to video should be on mute?
Video on, sir, please. Video on.
My video, you want my video should be on or on mute?
Yes, sir. Yes, sir. Your video should go on.
Okay. So please, I am testing. I'm sharing the screen. If you are able to see it, kindly tell me. Are you able to see the talk?
Yes, sir. Yes, sir.
Just a minute. I want a full screen. It shows full screen, but it's not.
No problem, sir. Visible, sir.
Visible, sir?
Yes, sir. Visible.
I'm not able to see properly. That's why I'm just.
It's visible, sir.
Visible.
Yes, sir. Visible. No problem.
Very clear.
Okay. So it's a full screen, huh? Is it full screen?
No.
Yes.
It is not full screen.
Yeah, just kindly give me 1 minute because I'm not. It's on view. How do I? Yeah. So now, is it okay, sir?
Yeah.
Okay. So very good morning to Principal Professor Vijay Prakash and our colleagues Tu Srinivas and Professor Ramakrishna. So first of all, thank you very much for inviting me to this webinar. Our friend Professor Ramakrishna indicated that this talk would be in the afternoon. Yeah, so I was forced, and then forced to see the AVN video. So I don't know whether it has brought back my memories. So now I'm a bit emotional. So I'm not sure whether I'll be able to lecture. Okay. So as you can see, I am an alumni of Mrs.AVN College, 1985 to 90, and I did my +2 and BSc. So I take this opportunity to dedicate this talk to all my teachers at Mrs.AVN College who taught me, because of whom what I am today. Okay. So am I audible or I have to be little shout?
No, it's okay, sir.
Okay.
Right, all right.
Yeah. So the title is indicating modeling mechanical behavior inside biological tumors. So many of you, we know it, we heard what is tumor. So when we hear of tumor, we get a very scary picture. And then if you go to internet, naturally, you will see, nowadays, when you sit in a film theater, so we have to understand, because there are a lot of complications. This is an attempt to make you little bit understand about modeling of tumor. And I apologize because the talk will start with some elementary things. Then I will spend some time on advanced things, what we are doing. Okay. So the outline is understanding tumor, then mathematical modeling on fundamental models on tumor growth. And once you talk about tumor, there is a lot of drug transport inside. So one has to also understand convection diffusion reaction inside tumor. So we spend some time on that. So then, suppose you start as treatment in tumor. So then whether the drug is completely spread in the tumor and then it is getting treated. So that is an important aspect. So this is called, if there are some necrotic core inside, so then treatment won't suffice. So we'll spend some time on this necrosis and then some mathematics. Okay. So I take this opportunity to thank Professor Rakesh Jain. There is a beautiful webinar. So of course it's pre-COVID, 2015. So I had got inspired from this gentleman who got a National Medical Prize of United States. So we have followed a lot of his literature. So those who are interested, they can spend some time on seeing this webinar. So now, what is tumor? So as you know, it's nothing but normal cells growing in an abnormal way. So as you know, people keep saying that it's an advanced stage. So most of the times the cancer is diagnosed at an advanced stage. So what is the cause of cancer? Cause of cancer is nothing but a tumor. But not every tumors are cancerous. So the early stage is non-cancerous, that is benign. And then advanced stage is cancerous, that is malignant. So now with a lot of technologies, you can take a good image. So I'm not telling how the image is taken. So if you see, this is a brain tumor. So it's a spheroid type of tumor, but then it can be irregular in shape. Okay. So now this is also typical images on the left of me. So this is called melanoma. So melanoma is a skin cancer. So it's a multicellular skin cancer. So that means I will talk in a while from now on what is the internal structure. So there are several cells, and then day 4, day 8, day 10, how it is growing. Okay. And the other one is a carcinoma. So if you see carcinoma, so there is a lot of gradient of the tissue. So this is the tissue. Tumor is nothing but tissue. So here, if you see the gradient, that means when I say there are cells and then this is a gray. So this is where I'm talking about. It is the core, necrotic core. So carcinomas are typically, these are on the tissues. So like kidney, lung, etc. So you get this carcinoma. Okay. So now, if you see a cartoon, okay. So if you see a cartoon, then it can be imagined like, suppose these are called vasculatures. Okay. So vasculature are nothing but the blood capillaries through which blood and other various liquids, fluids will be, liquids essentially will be transported to the tissue. Then there is a dark patch. So before the dark patch, so there is a small patches. So this is called a low in oxygen region, hypoxia region, and deep interior, it is a necrotic core. Okay. So this necrotic core is almost dead cells. Okay. So this is the invasive zone. Invasive means it is growing. It's growing. Okay. So we want to understand what is the growth. Okay. So we want to understand some modeling aspects. Right. Oh, I'm sorry, this is not working. Okay. So if you see the picture, blood vessels in glioblastoma, the brain tumor. So you can see such a complex network of vasculature. Okay. So by now you can guess it's very hard to model complete tumor because of the complex structure. Okay. So therefore, I would like to show you, these are the range. Okay, so this may not be 100%, but there is some range. So individual cells up to 65%, vasculature, that is a network of blood, okay, pipes, that is 5%, and interstitium, that means the network and then gaps, interstitium, up to 35%. So now you can see there is a very little possibility of nutrient transport into the tumor. The reason is vasculature percentage is only up to 5%. So therefore, out of the 100%, you have only up to 5% you can have drug transport or blood supply, etc. into the tumor. So therefore, it's very challenging to understand and then to come up with treatment mechanisms. Okay. So now, what is classification? So in vitro analogous. So that means it is in isolation. So you can say, what do you mean by tumor in isolation? Tumor in isolation, when I say, it could be an external on body or in a laboratory condition, it is in isolation. And what is in vivo? In vivo is surrounded by normal tissue. That means tumor is inside the body, okay? Or sometimes you take a small aspect ratios where you have tumor and sometimes you're operating as it is a human without taking the tumor out. So that is called in vivo. Okay, that means tumor is sitting in the normal tissue. Okay, so that is in vivo. So what we are interested? You see, I mentioned that there are blood vessels, there are healthy cells, there are dead cells. And this is also kind of blood vessel, but it is not blood vessel. So through blood vessels, solutes and blood come, and then it goes through these pipes, because these pipes are porous. So therefore, it goes through these pipes into the interstitium. What is interstitium? Interstitium consists of a lot of cells. Then whatever leftover fluids, they will be drained by these lymph vessels. Okay. So naturally, the resistance of this wall thickness, and then walls are porous. So that matters a lot. And also similarly, the lymph vessel wall porous, okay, that also impacts a lot, okay. And the cell interaction and other, these needle-like, they are the tissues, other tissues, okay. So it's quite complex. Therefore, modeling the complete scenario is, it's next to impossible. So certainly we start with elementary models and then slowly we go. So you can see this is a blood vessel in colon cancer. This is week 11. So the tissue is like this. Then week 13, week 16. So they are quite irregular. Blood vessels are abnormal. Okay. So this is a video. I took a picture. So those who are interested, they can refer the webinar by RKJ. So now, what are the things that are of interest? Naturally, the fluid flow and drug transport, we are interested. Then what controls the fluid flow and drug transport inside the tumor? It is nothing but the interstitial fluid pressure. Okay. So different tumors and the interstitial fluid pressure, it's in decreasing order. This N indicates some marker. Okay, so let's not talk about that. So what I'm trying to say is this is in mm per mercury. Okay, so in terms of that, so it's very important to understand that the fluid pressure inside the tumors could be quite high. Okay, so that's one point I would like to get. And what next? How porous is the tumor? That also is very important. Why? Because we send drugs. So whether it is reaching the tumor, whether the tumor is getting treated. So this is very important. So this is hydraulic conductivity of the tissue. So what do you mean by hydraulic conductivity? Suppose you take a sponge. So then if you pump in some fluid, so naturally it goes. Suppose you take a iron sheet and you try to pump in, so it won't go. So that means that is a hydraulic conductivity is mattering. Okay, so how porous it is. So as you can see, they're quite low. So they're quite low. Okay, so So can you unmute? Hello. So this is. So this is of the tumor. This is the hydraulic conductivity of the tumor, and this is the hydraulic conductivity of the normal tissue. They are quite low. Okay. So this is very important to understand. Okay. So now, what is the tumor dynamics? The first task is to understand cell doubling, right? So that means today so what do you mean by tumor? It's abnormal growth of cells. So today you have say 10 cells, tomorrow 100 cells, the next day 1,000 cells. So cell doubling is happening. So it is typically an exponential growth model. But do you think it grows and grows and it's forever? No, because there is a carrying capacity. So what do you mean by carrying capacity? In a given environment, that means in a given body conditions, in a given location where the first tumor started, it can grow to a maximum of some limit. It cannot grow beyond. The reason is you have, as the days pass by, I have indicated there will be a necrotic core. That means a lot of cells are dead and the other region is invasing, and there will be a compression, and after some time it cannot grow anymore. So there is a carrying capacity that matters. So carrying capacity controls the growth. That means there is a slowdown of the growth. So that is a logistic growth model. And what are the other things? Spreading and invasion. What do we mean by spreading and invasion? Today, a tumor is located in one part of the body that is called a primary tumor. After 100 days, you may realize it has occupied secondary sites and there are tumors in those secondary sites. So it's a complete self-organized biosystem. So you have motility of cells from one region to another region. So it's a complex model to understand. Okay. So what we are interested, the modeling community, and what is the need of modeling. So today, with a lot of technology at hand, the experimental costs are heavy. Okay. So therefore, the modeling necessity is to get some case studies and then study how the scenarios and then forecast so that the experimental costs are minimized. Okay. So the aim is studying growth, transport of drugs, blood-borne solute molecules, and identify critical issues. Okay. So that's the idea. So now there are different approaches. One is a discrete approach. That means these cells are discrete and it's a population of cells. So the cells interact, they grow. So it's a discrete approach, microscopic, very local phenomena. Microscopic means very local phenomena. But the other approach, I told you, it is very complex interactions. It's difficult to model. Therefore, let us not focus on the phenomena. Let us see from a distance. Means you are on a macroscopic. Okay, so that's a macroscopic phenomenon. That about the microscopic local phenomena, but on a large scale, you are seeing in an approximate sense. Okay, here we go. The first model. So, what is C? C is the density of cells. Okay, so density of cells, and they change with time. And what is the first model? It's very simple. dC by dt is alpha C minus beta C, where alpha and beta are constants. And what is alpha? Alpha is cell division, the growth constant. Beta is the death constant. That means the rate of death. So you have alpha minus beta C. The negative sign is because death. So now, since it is the same C, you can pull it as a constant, alpha minus beta. Now, which one will dominate? Suppose alpha is less than beta, so then the number of cells is exponential decay. So then if alpha is greater than beta, then exponential growth model. So therefore, this is called a constant growth model or exponential growth model. So very early studies, people try to understand just with that simple model. But I have indicated to you, there is a carrying capacity. Okay. What do you mean by carrying capacity? You cannot grow beyond. Okay. So why? Because I have just eaten now. I have then in 1 hour from now, I cannot eat more because I have some capacity within that. Okay. So similar analogy. So what is the carrying capacity? So you can see this. This is the benchmark I'm talking about, carrying capacity, the red dot line. That means your population of cells cannot grow beyond. Population of cells cannot grow beyond. So with time, now since there is a, so if there is a fast rate, it can grow like this, immediately stop there. It's a medium. Then if it is very slow, maybe curve can go like this, you will see. So here initial growth is very slow, then there is a fast growth, then comes the compression process and necrotic core. Therefore, towards the end, there is a slow growth. Okay, I have to choose the correct mouse, so that's troubling. Okay, so now, so this is a typical logistic growth model. Okay, so those who have studied in dynamical systems, they will be able to figure out it is a typical logistic growth model. So what is it? It looks like this. Okay, so it looks like this, the logistic growth model. So the rate of change of cell density, earlier it was constant times C. Now it is not constant, it is function of C. And how this function of C, so this is an example, logistic growth model. Okay, so this is a logistic growth model. If I have an eraser, I could have removed. I'm sorry for this. It's not going. Okay, so this is a logistic growth model. So K is the carrying capacity. Now, okay, so K is the carrying capacity and lambda is the rate constant. So you can see if lambda is small, the population growth is very small, but limited by the carrying capacity. If lambda is 0.5, if lambda is 0.75, very fast. It grows, then limited by the carrying capacity. So this is the typical logistic growth model. Okay. So now it's not simple. Okay, it's not so simple. The carrying capacity also may vary. Why? Because depending on various pathological conditions, the carrying capacity means today some capacity, tomorrow or 10 days you have different carrying capacity because various pathological conditions. Maybe already people have started the treatment for things started looking better, so the carrying capacity is changing. So K also is changing. Okay, so this is the first Hammond. Am I audible? Hello? Hello? Is it audible, sir?
Audible, sir. Audible.
Yeah.
Sir.
So K is also changing. So this is a combined. So earlier model, K is constant. Now K is changing. So therefore, if you combine, so you have a logistic growth model and K is changing. And not only that K is changing, naturally the carrying capacity, as I mentioned, carrying capacity will change with the treatment. Okay. So that means you're already taking some medicines. So therefore your carrying capacity is changing. So if you're taking chemo, okay, so that also affects because this is the treatment, one of the treatments for cancer. That is, you might have heard people have taken chemo, which is nothing but the immunotherapy, which enhances the immunity. So this is the impact of the chemo. Okay, so that means carrying capacity is reducing. It's good for us. Why? If the carrying capacity is reducing, the tumor growth is less. If the carrying capacity is more, then tumor growth is more. So therefore, chemo will reduce the carrying capacity, therefore the negative sign. So in modeling, you should know. Suppose I go to the first model here again. Okay. Suppose somebody is saying, I will put simply minus alpha C plus beta C. I mean, it does not make sense because both alpha and beta, we are assuming positive constants. So then you cannot put alpha C plus beta C. What happens if you put, it is nothing but alpha plus beta, it is some constant. Okay. So that is nothing but here I'm putting as single parameter. Now, depending on the sign of lambda, you can control. So you have to be careful. So here it is a linear model. So therefore lambda you can capture. But if you talk about this, if you put a chemo impact as a plus sign here, then what will happen? It gives a meaning that chemo is enhancing the carrying capacity. Therefore, with chemo, tumor is growing more. So that gives completely a wrong picture. Okay. So you have to worry about these things. So now this is the changing carrying capacity. Okay. So this is the changing carrying capacity and the logistic growth model. Always the logistic growth is bounded by the carrying capacity because that is the maximum. Okay. So these are elementary models. And what is the observation here? All these models are ordinary differential equations. So far, whatever I have shown you, they are completely ordinary differential equations. Okay. You can see dc by dt. So this is a coupled ordinary differential. Okay. Now, what is the drawback of ODE approach? Obviously, lack of spatial information. Okay. So why do you require spatial information? Because so tumor is of some size. Not only that, the behavior of cells in the invasive zone towards the necrotic core vary. So that is one point. So that means the ODE approach is not capturing the spatial information. And moreover, already I mentioned, you have a primary tumor in one location, then secondary tumors can be some other location. Why? Because the cells can crawl over tissue and they, through some receptors signaling, they will reach another host site and a tumor is developed in another location. So you need a complete spatial information. So ordinary differential equation approach does not capture this. That means one has to switch over to PDE approach. Okay. So towards this, let us talk about the first model. Those who are interested in learning mathematical biology, you can, oh, I'm sorry, this is 1990. Okay. So this is J.D. Murray. So there's a beautiful book. So you can study. So what is the typical balance law of any population? It is simple: production and various ways of production and various ways of death you balance. Okay. So here, the rate of change of tumor cell population is diffusion and proliferation. So here we are not talking about death. So what do you mean by diffusion? Diffusion means, so they are mobile. Okay. So they are mobile. So what is a diffusion? Okay. So if you take a small water, okay, in a glass and then put some ink drop. So water is still, water is still, you put ink drop. So then ink is getting diffused. So there is a motion, but it's only due to the molecular interaction. So it's no velocity of the water. Okay. So similarly, the cells are motile, so they move, that is a diffusion, and cells proliferate. That means they grow, multiple and grow. So if you balance, okay, this English is converted to math. What is English? Rate of change of tumor cell population. Okay. Diffusion, that is the total flux that is getting diffused, and net proliferation. Okay, that means growing. Now, growth is at what rate it is growing? That is the lambda, that is the proliferation rate, and J is the diffusion flux. Okay, J is the diffusion flux. So now, what kind of flux models are available for any mass flux? What kind of models are available? The simplest is Fickian diffusion. What is Fickian diffusion? It's nothing but Kirchhoff's law. Okay, so you have studied in physics, current at the junction. So similar. So the flux is diffusion coefficient times the gradient of the concentration. That means gradient of the cell density. So this is the Fickian diffusion. This is nothing but Fick's law of diffusion. Now, what I am doing, since J follows Fickian diffusion, divergence of J, so that is this. Divergence of J is this. And this is the proliferation. Suppose our D is constant. Okay. At this stage, when I'm putting inside the divergence, D diffusion can also change with space. Okay. That means, suppose you're talking about tumors next to a bone, far off from the bone, cells can really proliferate, diffuse, but towards the bone, because it's resisting, so maybe the movement is reduced. So D is depending on space. That is possible. Suppose D is constant, then you get this. Okay, so from math terms, so this is a parabolic PDE. Okay, so those who have done first course of PDE, so at least when lambda is 0, we have solved 1D model, and 2D also we can have analytical solution. Okay, so let me show you the 1D case, radial. Okay, so when I say generally 1D model, people may be under the impression line, but here, since it is a tumor, we are not talking about a line. We are talking about radial spherical symmetry. Okay, so that means it's a ball. 1D or in a ball means things are depending radially. Okay, so I'm assuming constant D. So then the Laplacian in 1D is in this form and lambda C is remaining. So now you give a no migration of cells beyond brain boundary. That means you have a tumor. Okay, tumor inside a, let us say, brain. So then beyond that, there is no. So R equal to 1 is the normalized boundary. So 0 and then some initial condition. And of course, at R equal to 0 also, you need some condition. Okay. So one can solve this analytically. Okay. But if it is non-uniform, as I mentioned, D is non-uniform, then it will be sitting inside. So then D is function of R. But then how do we solve? Naturally, you need some functionality of D of R, like diffusion is exponentially decaying or diffusion is a logarithmic growth. Something you have to have. So then things are complicated because you may not be able to get analytical solution, may or may not. Okay. So now if you see what is lambda, lambda is proliferation rate and D is the diffusion coefficient. Naturally, there is a competition between lambda and D. So lambda by D gives some control mechanism on how the cells are growing in a tumor environment. Okay. So such a simple model, it's only one equation, linear equation, but things are not so easy. Okay. So getting complete analytical solution in 2D, 3D is very, very difficult. So what are the methods that are possible on this simple equation? Analytical on some restricted cases, semi-analytical on some relaxed cases, numerics on more generic cases. But even when numerics fail, that means you're not getting converging solutions, then you have to do a complete analysis. Understand what is the impact of the regularity. That means or domains, how smooth a domain. So those things is an analysis part. Okay. So we will see some of the components. I won't be able to show everything. Analytical little bit. Okay. So maybe analysis we will see. Okay. Now I have plotted this particular model. When D is constant, this model is plotted. This is a credit is one intern student just last week. In fact, for this talk, I was preparing this. Now, this is R axis, this is the C axis. That means we are understanding how the cells are growing with the tumor radius. Tumor is like a ball. Okay. Now, lambda by D is 1. That means diffusion and proliferation, they are hand in hand. Okay. So, naturally, this is with time, because both are hand in hand. Okay, so as time pass by, so the concentration, the growth is reducing. Okay, because beyond some stage it cannot. So T equal to 2, 3, 4. I have written T equal to 2, 3, 4. Okay, so this is a very simple. One can plot in Mathematica or MATLAB. Now here, what we are interested in is different lambda by D. Okay, at a fixed T, different lambda by D. See, lambda by D is greater than 1 is the blue curve. So lambda by D is greater than 1. That means proliferation is more. So there is a rapid growth. So you can see there is a rapid growth, but due to the boundary condition, it has to come down because we are forcing fixed boundary condition. So therefore, it's a total conservation. So it has to come down. So similarly, if lambda by D is less than 1, that means it's a more diffusion dominated. Denominator is diffusion, right? Lambda by D less than 1. So diffusion dominated. Then therefore the proliferation means production is less. So therefore you have less concentration even at the beginning, okay, at the interior of the tumor, and then towards the periphery of the tumor, you meet the boundary condition. And this is the intermediate case when both are hand in hand, we have seen earlier. Okay. So these are simple 1D model. One can very much see and try to understand on a global picture, but not the complete interactions. Okay. So now, what is the need of simulations, numerical simulations? The need of numerical simulations is almost you are creating a parallel bio lab. Okay, so that's possible. So the picture that I have put, you might be wondering these are real pictures of a scan of a tumor, but indeed they are not. So these are virtual images. That means based on the data, they run complicated simulations and they have created virtual images of glioma tumor, that is the brain tumor. So this is a non-uniform diffusion. So you can see these are various cross sections, okay, view, different angle view. So this is at the diagnosis, and so this red denotes high density of tumors. There is a small red patch. On this angle, it is not visible, but on this angle, there is a little red patch. Okay, so this is the diagnosis and death at the time of death, how the intensity of the tissues, how the drug will be transported. So those things are predicted. Okay, so not only analytic, there is a restriction. Why? Because you can handle only maybe 1D. Okay, so not beyond. So simulation, you can go beyond, but then there are some challenges. Unless you have a data to verify, you won't be able to believe the simulations. Okay, so that's now you just not the diffusion and proliferation, but also the chemotherapy. Okay, so that is where the chemotherapy is added. Okay, So in brief, I have already shown this, but now, so GT is the temporal profile of the chemotherapy. That means it is changing with time. G of T is the chemotherapy function. What sort of chemotherapy function? That depends on the treatment. Okay. So again, you need a lot of mathematical models to test different G of T and see how the tumor is growing. Okay. So those who are interested, they can refer. Again, J.D. Murray is there. Okay. So, so it's a very lot of contributions by J.D. Murray to math biology. So now, so far only cell density we modeled. C, only one variable, right? So far, what is that? C, of course, in carrying capacity, there is a K, only two things. But I already told you, the tumor is very complex. You have cells, you have the pipes, that is the blood vessels, and you have interstitial tissues. Okay. So now the interstitial tissues, they have a large amount of hydrogen plus ions because they are controlling the growth mechanism of the tumor. Okay. So therefore, one has to understand not only the cell density. Okay. So one is cell density, another is the ions, then the extracellular matrix. What is extracellular matrix? In the gaps, there is a tissue now. In any body, human body, any part of the human body. So there are some tissues. That is called extracellular matrix. Okay. So now we have three things. One is cells, another is ions, another is extracellular matrix. So how the dynamics of these will interact. Now, suppose some friend is coming and telling dou C by dou T is something times C. Dou M by dou T is some constant times M. Dou nu by dou T is some constant times nu. If you write and say that this is my model of interaction, there is no interaction. Why? You are simply saying dou C by dou T is constant times C. Dou M by dou T is constant times M. Dou nu by dou T is constant times nu. There is no interaction. They are not talking to each other. Each one is independent. So you have to understand the proper interaction, how the cells are interacting with ions, how the cells are interacting with the cellular matrix, and translate that in terms of mathematics as a coupled model. So here C is cell, M denotes ions, nu denotes extracellular matrix. Okay. So now this model, which is given by Gettenbind-Gawelski, this due to lack of time, I won't be able to explain the complete physics, how these plus signs and then these negative signs are coming. Okay. But all that I can say, you have Laplacian anywhere sitting, that is a diffusion. Okay. And if you have a linear term sitting, it is simple growth or decay. Okay. So lambda times C minus M. What we are taking, lambda production and depth is the same. That is why you can see lambda C and lambda M. Okay. So lambda is taken same here. This is a growth of cells and this is a depth of hydrogen ions. Okay. So then you have gamma. So sorry, this gamma should be lambda. So that is rate of extracellular. This is gamma. Gamma is rate constant for the extracellular matrix. That is nu. Okay. And then how this model? So that depends on the tissue interaction, etc. So more details are available here. Okay. So all that I'm trying to say is the earlier model. It is PDE, but only one variable. What is the variable? Cells. Here, still it is PDE, more than one variable and coupled. So you can imagine it's very difficult to obtain analytical solution. Okay. So coupled ordinary differential equations, there is a lot of studies on stability matters, etc. Coupled PDE models, getting analytical solution is almost next to impossible. Okay. So even though linear, so they are not very friendly. sometimes we can, when I say difficult because of time, okay. If you drop in a steady process, maybe one can obtain some analytical solutions. Okay. So now, so far your big picture of tumor is a spheroid. You have fluid inside, you have tissue inside. So it is a porous ball. Okay. So now I want to make your life simpler by showing a very crude approximation. What is the first crude approximation we are doing? We are thinking tumor as a porous ball. Okay, laddu. Okay, so we are discussing how drug transport happens in this porous ball. So this is a contribution of my past PhD student. Okay, Jay Prakash. Now this is a ball. Now you are injecting drug. That means you are maintaining some constant drug periphery. It is getting inside and it is diffusing and convect. Okay, and there are some reaction because somebody is sitting inside the tumor and eating the drug. That is also there. So how do you model it? Okay, so it is a steady case here. So it is a steady case, and this you can identify. This is nothing but diffusion. Okay, so then this one is convection. That means you have some velocity. What is velocity? Blood flow velocity. So in a still glass, you put ink drop, it is diffusing. On the other hand, suppose you have a passive pathway of water pathway. It is flowing, continuously flowing. You put an ink drop, then what will happen? It will diffuse, but the velocity of the path also contributes. That is this velocity of the flow. And what is this fellow? Somebody is sitting, constantly eating. Okay, therefore the negative sign. Somebody is sitting and constantly eating the drug. So that is called the constant reaction. It can be non-constant also. Then what type of boundary conditions? Outside you are maintaining some fixed concentration. In mathematical terms, it's a Dirichlet condition. And if you are maintaining a flux, that is a flux condition, that is a Neumann condition. If you are combining a combination, that is a linear combination of flux and concentration, then it is a Robin condition. So there are possible types. Okay. So with this model, your equation, this equation is converted in terms of velocity is plugged in and then non-dimensionalized. So what do you mean by non-dimensionalized? You see, tumor has some radius. Suppose somebody is injecting drug on a tumor of this size, somebody is injecting drug on tumor of that size, and finally, end of the day, they realize that things are same in both. Then they'll come and make an argument, right? No. To get this result, tumor radius should be only 2 centimeters. Somebody will say, no. To get this result, tumor radius should be 10 centimeters. And both will come up with an argument. Indeed, both of them are correct. What would have happened? Some geometrical parameters maintained a constant ratio. Okay. Therefore, you are getting the same result. Right. So that is nothing but you do the dimensional analysis, identify the non-dimensional parameters. They will dictate the invariance of various geometrical characterization. So now, what are those? And also the flow characters and the diffusion process and convection process. What is the competition? Okay. So now this is a convection, diffusion, reaction. So each can compete with each, right? So Peclet number is convection to diffusion. What do you mean by convection diffusion? Velocity is very slow. That means it's a diffusion dominated. Velocity is very high. The diffusion has no role. Okay. So these are the aspects. And this is the Thiele modulus. That is the reaction to diffusion. So that means reaction to diffusion. So something is getting diffused, but somebody is sitting and who is eating much faster. So naturally, it is more reaction dominated. Okay, whatever you are giving, that means there is a possibility of starvation, because somebody is sitting inside and trying, yes, I'm hungry, give more drug. So then whatever drug you give, it won't suffice. So you will end up with starvation, then dead cells, then you will have problems. We will see. Okay. So then this, I just want to, because it's a mathematical modeling, that's why I just want to spend 1 minute on this equation. This is a grad C, that is nothing but very simple Laplacian. So Laplacian, you can convert this into an eigenvalue problem. So this is exactly the eigenvalue problem with this transformation, and this is the operator. So what I'm trying to say is linear equation, linear PDE, steady part. Okay. So then you are getting a simple eigenvalue problem. So you can obtain the eigenfunctions, which are in terms of the Legendre polynomials. Okay. So you get the eigenvalue problem and obtain the eigenvalues. Corresponding eigenfunctions are Legendre polynomials. Therefore, one can plug in this ansatz, that is Hn of R into Pn of cos theta. So then once you have this series, our job is to find these coefficients. So now for that, we define this inner product. Okay. Then project into the corresponding eigenfunction space, so that you get an ordinary differential equation. Even though I am putting partial derivative, this is nothing but ordinary differential equation for Hn, and using the inner product, you obtain. Okay, so the solution is obtained. So to some extent, linear models, you can manage analytical solutions. So that's my message. That's the reason I put. Okay, so linear models, you can manage your analytical solutions. Now, there is a competition of convection, diffusion, reaction. What do you mean by convection? Means continuously you are supplying drug. Diffusion means depending on the molecular structure, molecular diffusivity of the drug, tissue conductivity, how it is percolating, diffusion. Then reaction, there is somebody who is continuously eating. So there is a competition. Now, under what conditions you will have a starvation zone or a dead zone? This is very important. What do you mean by dead zone? Nutrient falls below a threshold value. That is called starvation zone. So there are two definitions of starvation zone. One is in terms of radius. That means you obtain a small inner radius of the tumor where the nutrient is below some threshold. Declare that radius as a dead zone. This is one way of looking at it. Another way is identify the parameter combinations for which C is below a threshold. So are you getting? Identify the parameter combinations. I don't want my C to be less than 0.1, let us say. Then for what parameter combinations my C is becoming less than 0.1, and declare that these combinations will give you necrosis. Another, identify the radius below which concentration is low. Okay, so that is the dead zone. Let us look at it. You see concentration profile with Peclet number. Increasing Peclet number means more drug is injected with high velocity. Okay, so now when you are increasing, okay, so the concentration levels are high. When the Peclet number 80, concentration is low. When Peclet number, if you further reduce below 80, there is a possibility that concentration becoming negative, which is not allowed. That means Peclet number 80 is the onset of starvation. Any Peclet number below 80 will give you low concentration. Okay. Now here reaction. Reaction, phi is large. Phi is large. That means somebody is eating continuously with a high rate. Naturally, there will be lack of supply of nutrient, so starvation. Okay, so this is parameter estimation of the starvation. This is not the radius estimation. We are identifying the parameters based on which you get the starvation zone. Okay, so this is the first order reaction. Okay, similar analysis. You can see Peclet number is a small, the concentration is less. This is the concentration, this is the tumor radius -1 to 1. Okay, on Z, we projected onto Z. So now this is with the Thiele modulus. That means high reaction, low concentration. Okay. Now, how do you estimate the parameters? Okay, you can define an optimization problem. What is the starvation? I already indicated to you. Minimum of concentration is 0 because we are making it approximately 0. We don't want concentration to be below something. Okay, so therefore this is the optimization problem. Then within this, you want to obtain the parameter estimation. Okay, how do you do it? So you get the Thiele modulus in terms of the Peclet number. Okay, so this is the Thiele modulus in terms of Peclet number. If our Thiele modulus is less than a critical value, then you are at the onset of starvation. So this is what we have done. Okay, so more details are available here. Here you can see what is that I am talking about. This is Thiele modulus, this is Peclet number axis, even here. Now, if you follow this curve, to the left of this curve, top of the curve, it is a nutrient starvation region, and this is a nutrient sufficiency region. Okay, so similarly here. Okay, so this is the classification we have done. So this is, it helps a lot so that you can identify whether the treatment is working properly. So if there is a starvation, that means whatever the drug you are giving, it's not sufficient. Why? There is a more powerful fellow sitting inside the tumor and eating continuously. Okay. So now we move on to, so this is one phase model. Only one velocity of the fluid is given to the convection. Okay. But tumor is not one phase, you have a multi-phase. So therefore, we are introducing the work by Hellenbein, Oxford. Okay, so two phases. What are the two phases? Cells and extracellular fluid. So these are the two phases inside the tumor. So that means the cells are moving, then also the extracellular fluid is moving. Okay, so yeah, let me show now. What is phi C? This is the volume fraction of the cells, and phi E is the volume fraction of extracellular matrix. And we are always maintaining a saturation assumption. Total volume is 1 always. Okay. Then what is the corresponding model? For any any physical model, the first one is mass balance. So we are doing the mass balance for the individual species. What are the individual species? One is the cells, another is extracellular fluid. Okay, so it is a typical conservation of mass balance, and here these are the corresponding source and sink. That means you have a net growth and death. Okay, it is given as a dump. Okay, so VC, what is VC? It is the velocity of the cells. VE is velocity of the extracellular fluid. That means fluid in the tissues of the tumor. Okay. So now what is the corresponding momentum balance? Suppose you have fixed law of diffusion. What is fixed law of diffusion? I told you total flux equals to, depends on the gradient from one place to another place multiplied by a diffusivity constant. Similarly, you take a sponge and you take maybe sponge, and then another one is maybe let us take brinjal, okay, and you inject some chemical into sponge and brinjal. You are expected in the sponge you have more larger pore space, so the drug is injected very smoothly, whereas in brinjal, even though it is porous, but it's a little closely, densely packed. So that is the permeability. Okay. So the simplest model I want to show you is it's a simple fixed law of diffusion model. That is nothing but Darcy equation. Okay. So what it is the total volume flux is varying proportional with the pressure gradient. K is the permeability. If more permeable, more volume flux. Viscosity of the fluid. If more viscous, less volume flux. Okay, so that is the thing. Now, this is for one phase. Now we want to extend it to two phase. That means you have cells and fluid. So natural extension is maybe you are putting V minus U, but there should be momentum equation for U also, right? So I am putting momentum equation for instead of that. So you can see a natural extension of Darcy equation, Vc minus Ve. What is Vc? Velocity of the cells. What is Ve? Velocity of the extracellular fluid and a corresponding pressure. Okay. So now momentum balance for the extracellular water. So you have two momentum equations now. So this you can visualize momentum equation for the cell phase, momentum equation for the extracellular fluid phase. Both are coupled. So this is the simplest model. Linear, steady, coupled model. Okay. This has to be supplemented with oxygen diffusion inside. Okay. Because there is the hypoxia region in tumor, that is a low concentration of oxygen. Then necrotic region, almost zero concentration of oxygen. So one has to also understand how oxygen transport is happening. So since the tumor, we are more interested in the interior, there is no convection because there is almost a dead core, no cells are alive. So possibility of convection is not there, only natural diffusion. So that is diffusion and some dump. Okay, so this is like consumption. Okay, so this is the necrotic core model. So you give it some boundary conditions. Okay, then try to, it's a spheroid model. Okay, it's a spheroid model, and we are analyzing these momentum equations inside the spheroid model. Okay, so you give some boundary conditions, okay, on the periphery, and then you set up a simple 1D model. Okay, so there are two regions we are classifying. One is outer region, okay, L of t to xt, and core region is 0 to L of t. You can see, even though the model is simple, there is a complexity to the model. What is a complexity? Not only it is two compartment, the interface is time dependent. That is a complexity. What is the interface? L of t is the interface. Why? 0 to LT is the core region. That means it's inside. On top of it, there is a tumor. Okay. So LT to XT is also tumor region, but this is the core region. So the model is 1D radial, but you have enough complication. Why? Because L of t and X of t are unknowns. Okay. So this is called moving boundary problem. See, typically we know that what we do, we are taking flow between parallel plates. So y equal to constant is my plate, force the boundary condition, solve. Okay, fine. Then R equal to A is my boundary condition on a sphere, force boundary conditions, solve, fine. But here it is not that. Here the boundary is moving and it's not prescribed. Once it is moving, it is not given. It should be part of the solution. You have to obtain. So it's quite complicated problem. So, so with subject to some boundary conditions, etc. You see, X is moving. Okay. Okay. So that's the most important thing. So those who are interested, they can see this paper by Chen and Bain. Okay. So now here, first one is the steady state, non-necrotic steady state. So R and XT. Okay, how XT is moving. Okay, so this is the moving boundary value problem. XT and RC of T is the interface between regions of cell birth and cell death. Okay, so that means you can characterize if there are healthy cells, then the cells will proliferate more. If there are dead cells, then naturally whatever little cells, they won't get sufficient nutrient, so they will die. So this is no necrosis. So there is only one compartment. Okay, but here there is inside necrotic core, then outside another core. So the growth model is stimulated and they have obtained. Okay, so you can see this is the necrotic core. With time, how it is varying. Okay. Interesting model. 1D, mind you, it is 1D, but all challenges are there because of moving boundary value. Okay. So now we move on to multi-phase model. Multi-phase model, 1D radial analytical solution, and not moving boundary value problem, fixed boundary problem. So this is one of my past students, Bivas from there. So he's right now at North Bengal Assembly. So now what we are considering such tumor. Okay. So this tumor contains the vasculature, that is the pipes, dead cells, healthy cells, and it is just a spherical case. So we are considering tumor in isolation. That means it's a complete isolated tumor. There is no normal tissue coating, and the tissue is, remember, in this multi-phase model of here, two phases, and they are just a fluid model. There is no solid mechanics here. Let me show you. Yeah. So there is one is a cell and another is water. So cells are moving. That means as a movement of the cells dynamics, and fluid. What we are considering, we are assuming that tissue is deformable. Naturally, tumor tissue is deformable. So tumor in the brain, tumor in kidney, tumor in lung, the tissue structure is different. The elastic parameters are different. Okay. So when do you talk about elastic parameters? When the tissue is deforming. When the tissue is deforming, right? So you are assuming that tumor is deforming. That means you have a fluid inside and it is porous. Fluid is exerting pressure on the pore space. Therefore, the tissue is getting deformed. Now, when the tissue is getting deformed, naturally there is an action-reaction law. So the tissue getting deformed will also obey some momentum balance. Okay. So our aim is now to fit a two-phase model. Okay. So VS, fluid phase velocity, solid phase velocity, volume fractions. This should be US, displacement. Then sources, interstitial fluid, and the densities. Okay. Now let me quickly go to the. This is almost what you have seen earlier. We are always assuming saturation assumption. This is called saturation assumption. What do you mean by saturation assumption? There is no loss of volume fraction. Okay. Total volume, that means some fluid may be converting to solid, some solid may be converting to fluid, but the total volume fraction is 1. That is this. For each phase, you write conservation of mass. That already I have explained to you. Now, what we are interested is conservation of momentum balance. We are interested in momentum balance, but before we do that, one can do a small algebra. You can just add subject to this constraint, then you get a composite velocity. This is a volume fraction multiplied by velocity, summation, this is called composite velocity. In any case, I have to skip some things. So let me show you the momentum balance equations. Okay. So now maybe some of the colleagues are not comfortable because it's more into fluid mechanics. So what are the typical momentum balance equations when we learn first course of fluid mechanics? They are nothing but linear momentum balance, which are nothing but. So exactly, we are also considering Navier-Stokes equation here. This is a corresponding inertial, okay, force. And these are the stresses, body force. Then this is interaction force. I will talk about this in detail. This is the interaction force. So this is nothing but balance, typical linear momentum balance. Okay. Now, what is this J denotes? J is F means fluid phase. S means then your immediate question would be: do you think your fluid and solid obey the same equations exactly? The answer is no. Do you think fluid and solid phase obey exactly the same equations? The answer is no. Definitely the corresponding constitutive equations differ. The corresponding constitutive equations differ. Okay. So for the fluid phase, so this is for the fluid phase. Okay. So I'm writing general equation. So the pressure forces, and these are shear forces, and so these are the first coefficient of viscosity. So now correspondingly for the solid also you have, but what is the major difference? The major difference is for fluid, the constitutive law is expressed in terms of velocity, whereas for solid, it is expressed in terms of displacement. Okay. So the structure, mathematically, the structure of the equations will be different. Why? Because if you see here dou Vf by dou T, but if you express in terms of displacement, Vs means 2 times the derivative with respect to displacement. Okay. So that therefore the structure of the equations completely change. Now, I promise you, I will discuss a little more on this interaction force. What is the interaction force? You have, so this is the tissue, then your fluid is going inside, then the tissue is deforming. When it is deforming, it will give a back force. So there is a action reaction happening. This is exactly the interaction force due to the relative velocity of the phases. That means you have a fluid phase velocity, solid phase velocity, then there is a relative phase velocity, and that obeys Newton's second law. The interaction force obeys Newton's second law. Okay. And also this force, interaction force, depends on the volume fraction changes. If at all your volume fraction is changing. Okay. Now, mu f is viscosity of the fluid, K is permeability, then you have elasticity coefficients, okay, then Young's modulus and Poisson ratio. So what are these? Why are these coming? If you are pure fluid, you do not have Young's modulus, Poisson ratio. So these are the corresponding elastic parameters. Since we are assuming that the tumor is also solid phase is moving, so we have the corresponding elastic parameters, which are Young's modulus and Poisson ratio. So one will denote the rigidity, so Poisson ratio, okay, and the other will the elastic nature, okay, Young's modulus. So Poisson ratio, roughly, let us say towards 0.49, then you will see almost it's a rigid, okay. So it's more. So now I make some preferred assumptions, then bring it to what are the unknowns for fluid velocity, displacement, the momentum equation for the fluid phase, momentum equation for the solid phase in terms of displacement, then
Sir,
yeah, now is okay. Hello.
screen sharing stopped, sir. Again, you can share it, sir.
Huh?
Please
I
share
will
your
share.
screen, sir.
Yeah.
Okay, sir.
Okay.
Okay, sir.
Is it audible?
Hi, sir.
Yeah. So the combined equations, okay. So now the unknowns are 3. You can see we have reduced to 3 equations. You don't do mass constants, and then yeah, we have, but when we use, we have saturation constant. The mass conservation is composite velocity. Okay. So what do you mean by composite velocity? It is giving the combined effect of the fluid phase and the solid phase. Okay. And this is of the solid phase. Parabolic and hyperbolic. Okay. Now it's an isolated tumor. What do you mean by isolated tumor? Literally, in experiments, they create a tumor in various animals. They take out the tumor with some veins intact and maintain ambient conditions and do experiments. So this is called the isolation. Okay. So what we are maintaining is the stress, normal stress, some ambient stress, solid stress. Once it is in a laboratory frame, we are not allowing the boundary to grow. So this is typically assumed. Okay. So you can test various other boundary conditions. Nobody is denying. And you need some initial conditions. Then non-dimensionalize. So I don't have enough time to explain the non-dimensionalization. What already I have given you Thiele modulus and Peclet number. Similarly, for this, you will get number of non-dimensional parameters. Okay, so you have to understand what is the need of those. What is the need of those is it's simple. Suppose somebody is maintaining a volume. I'll give one example. Suppose you take a pipe. Okay, pipe of some length and some radius, and you fill with water. The same water, I can fill it with a different pipe of different length and different radius. It's quite possible, right? That means what we are talking about is some quantity is invariant. What is that quantity? Maybe the ratio of length to radius. So similarly, in all these mechanical models, fluid mechanical models, you end up with a set of non-dimensional numbers which have their own meaning. Okay, so that's the point. Now, yeah, now it's a little more comfortable to see. Okay. Now 1D, if you assume, it's much more comfortable. You see, 1D, I am assuming Pxt is simply radial. Why radial? I already explained tumor is a spheroid, so radial distance 1D. So now it's 1D coupled equations. Okay, so one can try to solve, and time dependency is there, but still we managed to obtain the solution. Okay, so here we are plotting the interstitial fluid pressure with the time at different radius of the tumor. So now the interstitial fluid pressure is increasing, and it is more in the tumor interior. Why it is more? There is a less volume for the fluid flow. Why? Due to the necrotic core, the cells are dead and it is very hard. So you have a little volume. So therefore the fluid will have a lot of pressure. Okay. So that's very, very important. So maybe some people where they are feeling some acute pain, etc., maybe due to high pressure, which is constructed into the interior of the tumor. Okay. So here composite velocity. Okay, composite velocity. If you see composite velocity, if the composite velocity is high, then it is convective dominated zone. If the composite velocity is low, then there is no convection. That means if there is no convection, even if you inject a drug, it won't reach. So it is very much necessary to identify whether it is a convection dominated or diffusion dominated. What do you mean by diffusion? Naturally, it has to go. Convection means there is some blood velocities. Okay, so it can reach faster. Now, classification of necrosis with the different parameter combinations. So now somebody is deciding if my nutrient concentration is up to 0.3, then I will call it is a starvation. It is a necrotic region. Then you draw a straight line here. Parameters, the parameters above, that will be non-necrotic. Parameters below will give you necrotic. You decide what is your level of nutrient, you draw a straight line. Suppose somebody is saying, no, anything below 0.6, I will declare as necrotic. Then you draw a straight line. If you draw a straight line, all these combinations, these curve, giving all combinations, that is necrotic. Only this portion is non-necrotic. Okay. So it's very much required to identify the parameter combinations giving necrosis. Okay. Now you may ask, what is the sanctity of this model? You are saying you have got one complex model, you simplified, further simplified, and the model. Do you think this is big? So naturally, modeling in numeric, if somebody is doing numeric, is the first have to test some benchmarking cases. Okay. Here, it's 1D analytical solution very fast to clinical study. Okay. It's not exactly of the model that we have, but they have taken a tumor consisting of several islet radii. So there are small cells inside. So different islet radii they consider, and they have taken pieces, then they injected drug, and under luminochemosynthesis, they see the record. whether it has gone interior. Okay. Suppose the drug is not going interior, which means there is a necrotic core sitting. Okay. So we compared with their model, and you can see this is the clinical study with the different tumor isolate radii, and it's very competitive. Our comparison is very competitive. Okay. So you can see it's quite the behavior trend is very similar. Okay. So we cannot achieve exactly same because their operating conditions are different and all that. Okay. So with that, now what we have achieved is model. So first we have ODE model, PDE model, then single phase, then multiple phases, coupled PDE model we talked, then multi-phase fluid models we discussed. Now, just now what I presented is multi-phase fluid solid interaction. Okay, and solution. Now, what is, if the model is complicated, people go for numerical. Okay, so that's quite obvious. Most of the CFD community, what they do is they go for CFD codes and develop some numerics, right? But then how do you ensure that whatever the numerical results, they are some problem, high speed, okay, maybe applicable, but in a scenario like tumor, where the tumor shapes are irregular, where the boundaries are irregular, whatever numerical solutions you are giving, they may not using this. Before you develop numerical scheme, you see the corresponding the variational formulations and understand what is the richness it is demanding, what are the regularity conditions it is demanding, and then, so this is my last phase of my talk. So this is little heavy, but I'll keep it very simple. Okay, so those who are interested, that is we can exchange our emails. So this is mathematical analysis part, existence and uniqueness. So this is my current PhD student. So yeah, Monday he'll be giving synopsis talk. What is variational method? It's a developed weak formulation. Okay, that is valid for less regular functions. You are with me looking at the statement. Okay, so let me explain. Suppose you have a Laplacian, del square f equal to 0. Okay, Laplace equation. If del square f is 0, so then when do you say the solution is, suppose some h equal to is a solution of Laplacian? If del square h is 0, that means h should be differentiable at least 2 times. No, then only it can satisfy Laplace equation. If h is not differentiable 2 times, how can it be satisfying Laplace equation? Okay. But you will be surprised, there are solutions of Laplace equation which are not 2 times differentiable. Okay. So then how do you say that it is the solution of Laplace equation? So there is a concept called weak formulation. That means solution is not smooth. It's not as many times differentiable as the order of the equation, but still it will satisfy the solution in weak sense. What is weak here? Reduced regularity, reduced order. That means some fellow who is differentiable only 1 time, but still solution of Laplace equation. That is weak solution. Such solutions are possible. So here, such weak formulations are required to check the regularity. Okay. Then you talk about existence and uniqueness of these weak solutions. Then develop some numerical footing, work frame. Okay, based on mathematics, and people can take to the computer. Okay, so that's the step of algorithms, right? So what is the weak formulation? So you have to define some weak regularity spaces and the corresponding inner products, then define the weak formulation. So I don't want to scare you. So just you assume that we have a setup using which you can reduce the requirement of differentiability. That means if somebody is 2 times differentiable, I am reducing it to 1 time differentiable. And using the inner product, you convert the equations. We have 3 equations now, so 3 equations are converted. 1, 2, 3. Okay, so 3 equations are converted with the help of an inner product in these spaces. These are the spaces which I am talking. Okay, so I'm not in a position to give because this should be a different talk. Okay, so now how do you? So these are infinite dimensional spaces. So what is the next target? You project it to finite dimensional space with the help of a basis. For each space W, okay, so you define these basis functions, okay, that means x, x, m. This is for the pressure, this is for velocity, this is for displacement, okay. So corresponding to velocity, corresponding to displacement and pressure. Pressure is a scalar, these 2 are vectors. So then you propose the discretized version. This is called the Galerkin approximation. That means from the infinite dimensional spaces, you are coming to finite dimensional space. So that is the Galerkin approximation. Then you plug in, because it's time dependent problem. So you look for solution as a linear combination of these basis functions. Okay. So you have velocity, and now linear combination, coefficients are functions of time, because it's like your separation of variables, almost like your separation of variables. That's what we are working here. Displacement, pressure. Then if you substitute in your equations, you get system of ordinary differential equations. Okay, because you pick up the coefficients of the basis function, then you get a system of ordinary differential equations, and use the well-established theory for ordinary differential equations to okay. So I'm not explaining the complete technicality. It's a flow. What is the steps? I will show you. You formulate the problem. These are the equations that we have. 3 equations. Earlier I have shown you. So then you define an inner product space, and then with the help of that and with the help of these spaces, infinite dimensional spaces, you bring it to weak formulation. Then you project it to finite dimensional space with the help of this basis. Then propose the separation of variables. Then you get system of equations. Using the regular ODE theory, you can show the existence of the solution and when it has a unique solution. Okay. Then you are naturally interested in the stability, right? Once the solution exists and unique, whether the solution is stable or not. So for that, we are estimating some energy norms. So these are various energy norms that we have estimated. Okay. Then with the help of these energy norms, we declare that these sequences that we have projected onto the subspaces, so these are bounded. Okay, okay, these are bounded. So now once they are bounded, you can pass the limit so that convergence is established. Then correspondingly, we get such big theorem, which will indicate what are the conditions under which the solution exists and is unique. Okay. So then we have come up with a very innovative idea. You recall we have obtained 1D solution explicit, right? So that was by Bibaswan. We have obtained 1D solution. Okay. Using this 1D solution, we have studied various characters. Now we have a weak formulation. This is mostly theoretical, right? Nowhere you come across any solution. It is only theoretical. Okay. Then what we have done, we have combined our approach whatever 1D solution that we have obtained, that solution is plugged into these energy estimates. So that is the new contribution that we have. And using that, we have computed these energy estimates and we show the variation of the energy estimates. So now what is this dA? dA characterizes the permeability. dA characterizes the permeability. So if it is more permeable, so you can expect more convection. If it is less permeable, you can expect a convection is less. Okay. So this is the energy estimate on the composite velocity, right? So with the time, naturally, the velocity is approaching a stable uniform value. Okay. So up to some time, there is an impact of the Darcy number. Beyond that, so there is no impact. Okay. It attains a stable steady state values. Okay. So with Darcy number, you can see if the Darcy number, this is in increasing. Okay, increasing means the magnitude is multiplying. So that means so the Darcy number is low because 5 times means Darcy is low 5 times. 1, 2, 3, 5 is increasing. So 1 times 10 power minus 3, so more Darcy number. Then 2 times 10 power minus 3, it's much lesser. So with the Darcy number, the composite velocity is reducing the corresponding energy estimate. Okay. Now you have 2 norms we have defined. One is L2 norm and H1 norm. So corresponding regularity is hidden into those norms. So therefore, the behavior is also different. Okay. So then this is again composite in terms ratio. Okay. So 0.49 is almost like it is rigid. If it is a 0.2, so then it is deformable and it is not prone to necrosis. Poisson ratio 0.49 is prone to necrosis. Okay. So these are some characterizations we can study. So those who are interested, they can see these contributions. This is analysis, and this is the 1D solution with a comparison with the clinical results. Okay. So the conclusions, modeling growth, it is definitely a complex phenomenon. Okay. So if somebody wants to model the complete growth, you need supercomputers and complex models and not continuum based models. It should be completely based on discrete approach. Okay. Therefore, high computational cost is involved. Then it is very important to decide what are the parameter combinations which will say diffusion dominated and convection dominated, so that you are in a position to identify the necrotic zones. Then certain models, analytical tools are not sufficient. So you have to adopt semi-analytical or numerics. Okay. So the estimates that we have obtained, they give a direct idea. If you perform numerics, how things will look like. Okay. So and then the nutrient transport model, if you simply nutrient transport model, that means only it's a scalar equation. Okay. Even there, a lot of mathematics is to be explored. Okay. So what I'm trying to say is setting what we have developed, the corresponding weak formulation, this will be a benchmark to straight away go and do the numerics. Why? Those who are doing numerics using finite element method, finite volume method, their first step is to fit such a Galerkin approximation. So therefore, so here there is a Galerkin approximation. Those who want numerics, they can straight away use it and implement. Okay. So analytical, semi-analytical, numerics, but on top of it, analysis sometimes also is required to see what is the growth, behavior, etc. So with this, I have come to the end of my talk, sir, and if I am fast, kindly apologize. If you have any questions, I'll be happy to take it up. So thank you very much for giving me this opportunity.
So thank you, sir. So we are very fortunate to listen your wonderful and mind-blowing informative talk on modeling mechanical behavior inside the biological tumors. How the differential can involve to finding the behavioral mechanism of tumors. So I thank you, sir, on behalf of my college management and organizing committee of this webinar. So the participants asking you, sir, about the PPT, just you can share that PPT to my mail so that I can send the mail to if you have any objections. Sir.
Yeah, I will.
Sir.
I will.
We have a question and answer section for 5 to 10 minutes.
Yeah, no.
Unmute everybody. So just if you have any doubt regarding this one or any queries, just you can ask our resource person is a renowned professor. He can answer anything related to his talk. Thank you very much, sir.
Yeah, any questions? I'll be happy to.
So unmute all. If anybody have any question, just you can raise hand and ask questions. So Harshavardhan, Chandrasekhar.
కాన్పూర్ ఇది ఇక్కడ కాదు 1 ఏరియా వాళ్ళ పోతావా ఎందుకు నాకు తీసుకున్నావు ఎప్పుడో తెచ్చుకున్నాడా మంచి 4 ప్యాకెట్లు.
Sir, any questions related to this, sir? If you cannot have any questions, you can mute, sir. Anybody having any questions? Any questions from anybody?
No more questions.
Sir, good noon, sir. Hello.
Professor Tarpara asking, sir. Tarpara, you can unmute. Right.
Okay. Thank you very much, sir. Professor name resource person.
Tarpara, audible, sir.
Audible? Yeah.
Audible, sir.
Sir, congratulations, sir. Your vibrant presentation. That is, I'm something linked with modeling of cancer growth using stochastic processes.
Oh, I see.
My work is stochastic modeling on cancer cell growth.
Okay.
With mathematical assumptions. Mostly my work is matching with your work up to, I'm just using ordinary differential equations. I have not beyond that. I think I have not completely followed in between what I'm just understanding that you have extended the work to partial differential equations also, it seems.
Yeah, we do PE modeling.
Yeah. So I have a small question. It is not now when we are applying a mathematical modeling in a deterministic environment. Okay, though we are considering differential equations, we are assuming that in a happenings are in deterministic environment. In that context, I would like to listen you how best we can go for more nearer to practical possibilities. With is it stochastic modeling is more appropriate or math modeling, deterministic environment or uncertainty environment, which is to be considered more?
It depends on the particular case, because in particular these tumors are the characters, global characters of a tumor are well established. So therefore, many times whatever the researchers have done using deterministic models, they are able to meet the expectation. And you have seen we made a simple comparison with the clinical study, and we got a very good matching.
Yeah, you have considered some mostly empirical data, it seems. Am I right?
No. We have considered clinical data and compared
that is
with
what
our
empirical in the sense
analytical
practical
solution.
data.
Yeah. So what I'm trying to say is, even deterministic models for well-established cases, they give a good match.
Okay.
So based on the deterministic models, cancer treatment is on. And coming to your question on stochastics, they give for varied experimental scenarios. For example, people want to test some new drug which they want to test, okay, in the presence of some control mechanism, and then in the presence of, so they are changing the tissue structure artificially, etc. So then they have to bring in a stochastic model, and that has to be matched, and they can say that
yeah, if it is not out of occasion, in statistics we have some protocols. That protocols end up with verification of the model also.
Yeah.
Not only developing the model.
Correct.
The protocols is first in stochastic processes, we just identify the model, or we can say that it is building a model. After that, we use it to verify the robustness of the model. Finally, validity of the model also made it.
Yes.
Hope that if that type of things are there, more reliability on these models may be possible. It's just my opinion. You please.
Possible. Those who are working on stochastic, maybe they can. You see, whatever works I have seen on stochastic, theoretical sense, they develop theoretical model and they stop there. I have not seen a comparison.
Extensions are there for validity verification also. Validity verification also. Yes, you said. Yes.
Yeah, maybe. I have not. Yeah.
Anyway, it's a very nice work, sir. You have presented a very what we call it as with all clarity you have presented, and there is a ocean of applications to this differential equations. Really great, amazing. Thank you, sir.
Thank you. Thank you.
Any other questions? Any other questions? Please raise your hands and ask, sir. If there is no questions, we can close the morning session.
Okay, so
I think no questions, sir.
Okay, so
again,
thank you very much for inviting me and sharing my work. Okay.
So it's our fortunate, sir. So we thank you, sir. You readily accepted our invitation, and we thank for your cooperation for enter these suggestions for this webinar, sir. Sir, I thank all the participants for joining the morning session. So now the morning session is closed, and we have an afternoon session at 3 o'clock. Please join at 15 minutes before at 2:45, so that sharply we can start the session at 3 o'clock. At afternoon session, we have the eminent professor, Professor Rajasekar sir. Is a former Vice Chancellor, Dravidian University, and he has many awards. He had many awards and rewards. He's nothing but he's a diamond in a crown of mathematics. So thank you very much, sir. So we close the sessions, the morning session.
Thank you to all participants for listening.
And thank
you so much.
especially Rajasekar sir, and other participants.
Thank you.
Okay, NRK. Okay.
Okay.
Thank you.
Yes. Hello.
Hello,
NRK.
Right. Bye. Anything to say?
Okay, sir. Close, sir.
Close. Phone మాట్లాడదాం.